In this lesson, we're going to look at some basic electrical. So I know you would have done electrical last semester before you went out for OJT. So this section should really be a fairly quick review. Electrical was added as a component to your math course when electrical was covered in second semester. But what I've discovered from year to year is just because you've covered it before doesn't necessarily mean you remember it. And the other thing I found is that the problem solving strategies we use to solve some of the circuits, especially when I get to series combination circuits, really help with problem solving in other areas. So you can think of it as mental practice in problem solving as well, but it also has practical applications. So this first lesson, we're going to look at Ohm's law and the power law, which should be quite familiar to you, some basic rearranging. If you forgot any of your electrical from last semester, it's going to give you a good refresh on it. Electrical questions are something that you will have show up on your block exam. And while they may not be worded exactly the same, being able to take current and voltage and resistance and work with those is going to be important. My husband happens to work in wastewater treatment, and while he's not an electrician, they have to understand how electric pumps work, much like you would have to understand how electric fans work. And unfortunately, one of his exams, his third block exam, he came home kicking himself because by the time he got home from his exam, he says, I know for sure. He says, I made a mistake converting from milliamps to amps. He says, I did 100 instead of 1,000. I know I got that question wrong. And he was so bummed when he got his results from his exam because he had a 69 instead of a 70 and they didn't round up. So just refreshing and reviewing those things are important, and there are things that you will see even if it's not something you necessarily would calculate every day on the job. So first of all, I'm going to review the electrical terms. These should be familiar to you. So we have voltage, current, resistance, and power. So voltage is energy that results from separated charges. So atoms have positive centers, and then they have these negative electrons. And electrons can actually float around. Now, this is where my chemistry geeky bit comes in. So those electrons can actually be pulled away from an atom, and basically, chain reaction, they can be transferred down a line. That's what causes current to flow. So metals are really good at sharing electrons, and because they're really good at sharing electrons, they have lots of electrons in their outside shells that aren't tightly bound to their middles. They can migrate electricity down a metallic wire. That's one of the differences between something that's an insulator that does not allow electricity to flow and something that does allow electricity to flow. All right, so it's how well do they allow electrons to be pulled away from their positive middles? So you can think of it like a planet system. You've got a center and you've got these orbiting electrons around the outside. And for electricity to flow, we have to kind of pull them away and pass them on to the next guy, and then pull the next one. And it's like a chain reaction that works down a wire. So that separated charge creates, when we pull an electron off one thing, what it results in is a slightly positive on this side, and that electron wants to make its way back because it wants to neutralize the charge. Okay, so we have a separation in charges, which results in a push, much like a magnet. If you have two magnets and you bring them together, they'll want to attract. That's the same thing with electricity, and that's what results in voltage. So we say it's energy from separated charges. That's what occurs. That's kind of the loose definition. Sometimes we call it electromotive force, and that's because electrons moving creates a force or requires a force. So you will see the word electromotive force. Now, I'm not sure which term Alex used. Sometimes in equations, you will see voltage written as V. Sometimes you'll see it as V because the units are volts. That's how we measure voltage. Sometimes you will see the letter E used for voltage. And E comes from electromotive force. I used to always puzzle over why sometimes, and it's trade books especially, use E for voltage, and that's because of electromotive force. Now you will find I flip back and forth between the two. So for this lesson, I'm going to stick with E because that's what's in your books. And for the most part, I will try to stick with E for consistency, but you'll get the occasional V popping in. It's your choice which one you use, as long as you remember that voltage can be electromotive force, which is represented by E, or by V for volts. Current is the flow of electricity that we have happening. So it's how fast are those electrons being transferred. Now, current always requires a closed loop in order to flow, and we measure current in amperes after Mr. Ampere, who discovered them. Resistance is measured in ohms after Mr. Ohm, who discovered resistance. We name a lot of things after people. Resistance is just the ability of a material to slow the flow of electricity, or to resist the flow of electricity, if you want to put it that way. So resistance stops electricity. So if you are resistant to doing homework, you will stop doing homework, or you will be less likely to do it. So something with a high resistance is going to impede or stop the flow of electricity. And then we have power. Power is measured in watts, and it's the rate at which electrical energy does work, and it's equal to joules, which is energy, per second. So it's equal to energy per second, okay? Now that we are going to use that equation today, just at the end of the lesson. We won't use the power equation a huge amount in our calculations, but we will use it. We'll use it at the end of today. So you'll notice all of the units here, they don't have milli or kilos in front of them. They're in their base units. These are all considered to be metric units. But when calculating with them, we are going to have to make sure we're using volts, amperes, ohms, and watts. If you were given something in millivolts, change it to volts. If you're given milliamps, change it to amps. If you have kilo ohms, change them to ohms. You have to work in your base units for your formulas. That's going to be really, really important for the electrical units. All right, so it's just some common symbols. You've probably seen a lot of these before. You should be fairly familiar. We use a line for a wire. Switches often look like this. A cell or a battery we'll often see like this. If you see that symbol, that means we're dealing with a battery. You guys won't deal with batteries so much, but you may see this formula, and sometimes it'll say 120, and that means 120 alternating current. This is a source. So that would be the equivalent to having a battery, but it's alternating current that would come from the wall. So because automotive technicians, they deal with batteries all the time because we don't plug our cars in, really. I guess we're getting more and more cars that plug in. But for you, you're going to be hooking up to an electrical panel in a house. And for the most part, you won't have to deal with battery. You will be dealing with alternating current. But our math for this part is works the same way. Okay. One of the things that you'll want to keep in mind is sometimes you will be hooking up to batteries. You may have battery backup, in which case, if you're dealing with battery backup, oftentimes you'll see these symbols come into play. A cell is just a single cell, and oftentimes batteries are made up of more than one cell. Same way we put like 3 batteries in or 4 batteries in a toy or something like, or a tool or something like that. And that's where this here battery with multiple cells comes from. A lamp can be a circle with an X through it. It can also be a circle with kind of a little loop in the middle. So those are two versions of that. Voltmeter. If we're adding a voltmeter or showing where we're measuring voltage, we'll use a circle with a V, ammeter circle with an A. Resistors can be drawn 2 different ways. My preference is the squiggly line, but that's what I learned with. So that's what I tend to use, but you'll sometimes see them this way. Variable resistor, we use those for switches, and then a motor. Now you're going to see different things in your trade. Sometimes they'll be labeled with what it is, but those are the common ones. By the end of our electrical section, you'll have added a couple more. One of them, you'll add a transformer, which is 2 coils, kind of like this. That's a terrible drawing. We'll get there when we get there. We'll deal with the transformer, and that uses electromagnetism. I know you guys will deal with transformers because I was looking at the wiring diagram for my heat pump. The first thing I noticed was, oh, we've got induction happening here. There's a transformer in it to change the voltage and change the current to the fans. So I know you're going to deal with that, guaranteed. Whether you calculate them or not, I'm not sure, but I know they exist there. So we will see transformers, but we won't see transformers until just before you guys head out for February break, which is coming fast and furious, down to 3 weeks. All right, so Ohm's law, we're going to start there. So Ohm's law is voltage E is equal to current times resistance. Now there's a really good video I posted, and I apologize, it's a little bit elementary. You may have watched it already. If you've watched it already, it will give you, it's demonstrated Ohm's law compared to water. It's a fabulous video, even though it's simple. I find it just explains everything so well and in a way that you can see it, because we can't see how electricity flows in wires. So it gives you that kind of qualitative understanding. So voltage is the push that pushes current through our wires. Resistance is what slows that current down. So current can only flow through this wire as fast as it can flow through the resistor. So voltage and resistance control our current. If we know how much current and how much resistance, we can calculate our voltage. Remember last semester we talked about directly proportional quantities and indirectly proportional quantities? So I'll give you a couple tips. If we increase voltage, that means we're going to get an increase in current, assuming we don't change our resistor. They are directly proportional. They're both going in the same direction. So an increase in voltage results in increase in current. I'm going to erase that, and we'll throw another one in here. What if I have the same voltage? Okay, I'm not changing voltage. It's the same voltage coming from the wall. If I have more resistance in the current, well, resistance slows current down. If I have more resistance in the circuit, current drops. So current and resistance are inversely proportional. To get more current, I have to decrease resistance. So those are just a couple of little pieces. Voltage and resistance will be directly proportional if the current stays the same. So if we want to keep the current the same, if we increase voltage, we'd have to increase resistance as well. So basically, if they're on opposite sides of the equal sign, they're directly proportional to each other. If one increases, the other increases. If they're on the same side of the equal sign and multiplied together, if one increases, the other has to decrease. So they're inversely proportional. The terms aren't so important as much as that you understand what happens, and you can always test what happens using numbers, and you'll have a couple questions where you have to test what happens. Now let's just look at this little diagram with water supply, because I find it gives a good visual. The water supply here, so we have water supply, we have a push coming from a tap or a pump. So this is like our voltage. That's like our battery. The hose acts as our wire. It allows current to flow, and a nozzle is like a resistor. If you close up the nozzle, so you're increasing resistance to water flow, you've got less flow. If you use that analogy, I find oftentimes it helps us understand what happens in a circuit. As we increase the resistance, we should get less current. So if you want to think of it like a hose and a nozzle, that can be really good to help you visualize if you're somebody that just doesn't really get how the electrical component works. All right, so we're going to do a few calculations, but we're going to start first by rearranging the equations. Now I'm going to have you rearrange the equations the mathy way, but I will give you the triangle formula as well. So E equals IR. Voltage equals current times resistance. What are two other ways that Ohm's law could be written? Well, we could write Ohm's law with I equals. So we could write Ohm's law in terms of current. Current is equal to, if I want current alone, I need to get rid of resistance. So you would divide both sides by resistance, because we have I times R and the opposite is division. So we'll have current is equal to voltage divided by resistance. We can also write Ohm's law as resistance equals E over current, voltage over current. So just simple rearranging. Now there is a triangle that if you don't know the triangle yet, or you didn't cover the triangle, I'll give you the triangle version. I really don't like it because it is a shortcut and it doesn't really explain the math. We have a triangle here. We're going to put our formula into it. E is all alone, so we're going to put it on the top all alone. I and R are next to each other, so we're going to put them on the bottom. Okay? This line here represents multiply. So current equals, or voltage equals current times resistance. In order to rearrange our formula, just cover up the letter you want to find. So if I want to find voltage, so we'll cover, if I want to find voltage, I cover that up and I'm left with I and R. I'm going to get my little eraser here. Okay. What about if I want to find, I think I have a highlighter here apparently. If I want to find current, I cover up current and I'm left with E over R, or E divided by R, which is what we have here. Okay, so we can use that in order as a tool if you want. I will allow you to use it even though it's not my favorite method. All right, now we're into doing a few calculations, and let me get rid of my highlighter because we want to draw a few things. So example 1, I want you to sketch the circuit using some common symbols. So I just want you to think about symbols and calculate the current in the circuit in milliamps. We're going to do a few conversions in here just to get you used to doing those conversions. So to sketch the circuit, a battery is a series of long lines and short lines. The long lines are the positive side, the short lines are the negative side. How I remembered that is a negative sign is a short line. And then you're going to have a wire, and then we're going to throw a resistor in. This is why I tend to copy and paste diagrams before. We have, oops, that's not a 2, that's a 470 ohms and 12 volt battery. Current is going to flow through this wire around the circuit. Now, current used to be defined as flow from positive to negative, but now we understand current, actual electron flow is from negative to positive. But the old conventional current of saying current goes from positive to negative has stuck, and I don't understand why they haven't changed it. Old habits die hard. It's kind of like sticking with inches, even though we're supposed to be metric. So now we can do our, so that's just a quick practice drawing. Now we're going to calculate the current. So voltage, you can use your triangle if you want, but voltage is equal to current times resistance. If I want to find current, I'm going to divide both sides by R. And we have current, that cancels, equals voltage divided by resistance, which is equal to 12 divided by 470. Notice I'm using volts and I'm using ohms. If I'm using volts and ohms, we are always going to get the base unit out. So I'm going to get amps as my answer. If you put that in your calculator, you get 0.0255 amps. And there are 1,000 milliamps in an amp. So we're going to multiply by 1,000. And we find we have 25.5 milliamps. Much easier to say 25.5 milliamps than it is to say 0.255, which 2.5 what? That's just a little number. There's something about saying it in milliamps. It's often easier to understand. All right. Example 2, calculate the value of the resistor in kilo ohms. I know that looks really weird with the 2 O's in the middle, but that is how it's spelled. In kilo ohms, given that the ammeter measures 45.56 milliamps, and the voltage across the resistor is measured to be 110 volts. So 110 volts here. All right, and at the ammeter, we have 45.56 milliamps, which there's 1,000 milliamps in an amp. So that's equal to 0.04556 amps. Knowing how to go back and forth between those. So in this case, we're dividing by 1,000 to go from milliamps to amps. Remember those metric conversions. You'll want to know those. Okay, so now we need to do our calculation. Now the current in this wire is the same current that's going through the circuit. We're going to see in our next section that if we connect things with a single wire, so a single line, there's only one path, the current is going to be the same the whole way through. So the current here would match the current through the resistor. So again, E equals IR. I'm looking for resistance, so I'm going to divide by I. Resistance is equal to current or voltage divided by current, which is equal to, we use 110, divided by, and you have to use amps, not milliamps. That leaves us with an answer of 2,414 ohms. But I asked for kilo ohms. The reason we asked for kilo ohms is this is a very large number and we can round to one decimal place. I know I didn't specify. That happens to be equal to 2.4 kilo ohms. So again, it's just to go from ohm to kilo ohm, we divide by 1,000. It's like meters and kilometers. Okay, if you have any trouble with those conversions, let me know. I'll give you a quick refresh. You also have access to the videos from last semester. Feel free to go back and watch those. If the ammeter measures 12 amps and the resistor is 15 ohms, what's the voltage supplied by the current? So we have E equals IR. So we know we're looking for voltage. We know our current is 12 amps. We don't have to convert it this time. Whoops, not an equals, that's a times 15 ohms. 12 times 15 gives us, helps if I'm on the right page, gives us a voltage of 180 volts. That's a nice, easy question. Maybe I should have led with that one rather than conversions at the start. Example 4, the power source in a circuit. So this is that little AC symbol I was referring to, alternating current. An itchy nose here. So if you see that symbol, that's our voltage source. It's marked with V for volts. It could be marked with an E for electromotive force. Both of those would be your power source. So the power source in a circuit shown supplies 120 volts. What resistance would result in the fuse or circuit breaker tripping if it's rated for 15 amps? So we need to figure out what is the resistance that goes with 15 amps. So we have E equals IR. And to find resistance, I divide by current. So resistance is equal to voltage over current, which is equal to 120 over 15, which is equal to 8 ohms. Now let's think about what happens. So what resistance would make the fuse trip? So the fuse is going to trip, or it's going to melt, once I get to 8 ohms, okay? Or once I have, it's safe up to 8 ohms, we'll put it that way, okay? Or safe up to 15 amps, so it's safe at 8 ohms. If it's gonna melt, will it melt if I'm over 8 ohms or if I'm under 8 ohms? So let's think about what happens. So a circuit breaker or a fuse is going to cut power in the circuit, or it's going to break the circuit whenever the current goes over 15 amps. So let's think about what happens. E equals IR. Okay, the voltage is not going to change. If my resistance increases, so it's 8.5 ohms, my current has to decrease to keep this the same. So if I have more than 8 ohms, we have less current. I'm going to call it less A for current, okay? We have less current, so it's safe. But if I do the same thing, if we decrease the resistance, so there's less resistance, the current would increase to more than 15 amps. If we have less than 8 ohms, then we're going to have more than 15 amps. So this is the scenario. We would have to have less than 8 ohms for the breaker to trip. it's not difficult, but it's one of those ones that you kind of have to think a little bit through which way is it going to go. It's easy to flip those around. Maybe that's just me and a left-right dyslexia thing. I like to sketch them out and think about what's going to happen. All right, power law. It's the last piece for this lesson. So 2 simple concepts should be really quick for you to do. So power is the amount of work that is able to be done by current, okay? Or by voltage. Think of it that way, by voltage and current combined, maybe we want to think of it. So power is how much energy we use per second. So the more power we have at our pump, the further the spray is going to go, okay? Or the more current we're going to have. So more power results in more current, okay? More power is also going to require more voltage if the current doesn't change. So we have those things, because power is directly proportional to E and it's directly proportional to I, but voltage and current, if the power stays the same and the voltage goes up, the current's going to have to go down. And we're going to see that when we deal with transformers a good little bit. All right, joules is a way of measuring energy. So if a question ever asks you how much energy is used by a 1500 watt light bulb, or I guess you're not going to have that much, 1500 watt heater. The energy we measure in joules, even though we bill energy in watts. That's what you're going to see on your power bill. All right, so just a couple ways that we can write it. It's the same as before. You can put it into a triangle. I won't explain how to use the triangle again, but power is alone, so it goes on the top, and it's E times I. They're next to each other, so they go together. The 2 other ways we can write the formula, we could say voltage is equal to power over current, and then current is equal to power divided by voltage. Okay, so those are our 2 ways of writing it. Now, just a quick calculation with these. How much power is used by a light bulb which draws 3 amps from a 12-volt battery? So how do we figure it out? Well, simple calculation. Power is equal to voltage times current, which is equal to 12 volts times 3 amps. Again, we're using our base units, which gives us 36 watts. Power is always measured in watts, again, after the person that discovered it. How much current is drawn by an LED bulb rated for half a watt that draws 12.3 volts of power? So this is like a light bulb used in a vehicle. So again, we're just rearrange our formula. Power is equal to current times voltage. We want to find current, so we're going to divide both sides by voltage. They cancel. So we have current is equal to power over voltage, which is equal to 0.5 watts divided by 12.3. And we have 0.0407 amps, which is equal to 40.7 milliamps. It's nice not having to write the leading zeros. And one final question. What's the resistance of a heater that draws 1500 watts of power from a 12-volt source? This question's a little bit tricky, only because you kind of have to think about 2 steps. So if I want to know resistance is in the formula E equals IR. The problem is I have E, but I don't have current. I have power though, and power is equal to E times I. If I know power and voltage, which we do, I can get I. So that's what we're going to do. So current is equal to power over voltage, which is equal to 1500 watts divided by 120, which gives us 12.5 amps. How much resistance does that heater have? Well, we're going to plug that in over here. We know our voltage. We want to know resistance. So resistance is equal to voltage divided by current. Let you work at rearranging that. Which voltage? We still have 120 volts from our plug. Current, we calculated at 12.5 amps, which leaves us with 9.6 ohms. So pretty easy to calculate. B says if the heaters run for 1 hour, how many joules of energy will be consumed? Well, a watt is a joule per second. So in order to figure out how many joules of energy we use, so a watt equals a joule per second, we would have to multiply by time in order to get rid of it. So 1 hour equals 3,600 seconds. So we could say that this is a 1,500 joule per second heater times 3,600 seconds, excuse me, which is equal to 54 million? No, 5,400,000 joules, which we would better write as 5,400 kilojoules. All right, so this isn't too bad. This is just using the formula where power is equal to, or energy is equal to power times time, okay? And you don't really use that formula too much. There is one of those questions in the practice, so I threw one up here just so that you know what to do when you got to the practice, but you won't see that show up too often. So hopefully that's a quick refresh of Ohm's law. Hopefully that brings back some terminology that you covered with Alex. If you have any questions about it, please don't hesitate to let me know. We're going to use Ohm's law quite a little bit, so make sure you're comfortable rearranging those equations.